The Lagrange, or Taylor Error Bound, Part 3, more examples. Let f of x equal the sine of x over 2 minus pi over 4. And let's approximate f of 0.4 using the third degree polynomial approximation about x equals 0. So we're going to find our third degree approximation, which means we need values of the function and its derivatives. So f of x is a sine. F prime of x is cosine, but I have a chain out of a half. In fact, we'll have a chain out of a half each time. I get 1/2 cosine of 1/2 x minus pi over 4. And then f double prime is negative 1/4 sine of 1/2 x minus pi over 4. And f triple prime is negative 1/8. Don't forget we have a chain out every time of times 1/2. So negative 1/8 cosine 1/2 x minus pi over 4. And I could stop there, but I know the second part of the problem. So I will need to find the fourth derivative as well. 1/16 sine of 1/2 x minus pi over 4. And we're going to find values at the center. The sine of negative pi over 4 is negative root 2 over 2. The cosine of negative pi over 4 is positive root 2 over 2, but we have an extra times 1/2. And then f double prime of 0 is negative 1/4 times negative root 2 over 2. F triple prime is negative 1/2 times positive root 2 over 2, and we can stop there. At least when we're finding values. But I will make a note that my fourth derivative, taking the absolute value, is always between 0 and 1/16. We'll use that for part B. But now I want to approximate my function. So f of x about x equals 0 is approximated by my third degree polynomial, which is f of 0 plus f prime of 0, root 2 over 4 times x minus 0. And then I have plus, let's see, root 2 over 8, it's going to be positive, times x minus 0 squared over 2 factorial, which is 2. And then minus root 2 over 16 times x minus 0 cubed over 3 factorial. I'll go back and put the factorial right there. Which means that f of 0.4, because that's the value that we want to approximate, so f of 0.4 is approximately negative 2 root 2 plus root 2 over 4 times 0.4 plus root 2 over 16 times 0.4 squared, and then minus root 2 over, let's see, 16 times 6, and then 0.4 cubed, whatever that decimal is. But let's look at part B, which says, let's find an upper bound on f of 0.25 minus the approximation of 0.25. And if you recall from part 1, I'm looking for an upper bound on the error. Now, if you don't remember or recall that that is the error, this is a huge clue that we're looking for an error. Not perfectly, because I could be looking for an upper bound on the function, but this back part tells me it's an upper bound on the error. So the upper bound, using my third degree polynomial, is no more than the maximum of my fourth derivative times x minus 0 to the next power 4 over 4 factorial. The only thing I'm missing is the max, but we already saw that right here, that the max is 1 over 16. So I can put 1 over 16 times 0.25 to the fourth over 4 factorial, which is, and I did the work to get this 0.00001017 plus some more decimals. Let's take a look at a numeric example. Suppose that f of negative 3 is 2, f prime of 3 is 5, and then the nth derivative at negative 3 is 2 to the n for n between 2 and 4. Let's find the fourth degree approximation to f about x equals negative 3. So I could say that f of x is approximated by my fourth degree polynomial, which is f of negative 3 plus f prime of negative 3 times x minus negative 3 plus 2 to the 2, because my second power, or my f double prime of negative 3 is 2 to the n. So 4 times x plus 3 squared over 2 factorial plus 2 cubed times x plus 3 cubed over 3 factorial plus 2 to the fourth times x plus 3 to the fourth over 4 factorial. And we could simplify that, but I will leave that as is because I have found a fourth degree approximation to f about x equals negative 3. Now for this problem, I want to find bounds on f of negative 4 using my fourth degree polynomial approximation, given that the fifth derivative is always between 0 and 120. So I'll leave my f of x up here so we can see this. So I can say that f of negative 4 is approximated by t sub 4 at negative 4, which is 2 plus 5 times negative 4 plus 3 plus 4 over 2 factorial, I will simplify that down to 2, times negative 1 squared, plus 8 over 3 factorial, okay, 3 factorial 6, simplify more if you want to, times negative 4 plus 3 cubed, plus 16 over 4 factorial, which is 24, times negative 4 plus 3 to the fourth power. I did the work a little bit earlier and found that t sub 4 at negative 4 is negative 5/3. So what are the bounds on f of negative 4? Because remember that this is the approximation for my function at negative 4. It's not the exact value necessarily, and probably not the exact value. Well, I know that the remainder, using my fourth degree polynomial, is less than the max, okay, 120, given right here, times negative 4 plus 3 to the next power over 5 factorial. Well, negative 1 to the fifth power is negative 1, but the absolute value gives me positive 1, which gives me 120 over 5 factorial, but 5 factorial is 120, So my remainder is no more than 1. So what are the best bounds on f of negative 4? Well, we know that f of negative 4 is approximately negative 5/3. So I could put f of negative 4 right here. And I know it's no more than negative 5/3 plus my error. But it's greater than negative 5/3 minus my error, because the error is the most I can be away from the actual answer, which tells me that f of negative 4 must be somewhere between negative 8/3 and negative 2/3.